So today we will discuss about one more important concept which is referred to as precision rectifier. All of you know what exactly we mean by a rectifier, right? So most of you have worked with these things. I think all of you have worked with the rectifiers in different contexts, right from your first semester, even in your analog electronics and all, right? When you use devices used to convert AC to DC, here the specific adjective here, the precision rectifier, right? So now when I start discussing about a typical rectifier, right, a very conventional example, I will take a half wave rectifier, something like this. So when I have got the load resistance here, right, if this is your V in, this is the diode, and if you take this as VL, the load resistance, right, or this is the load resistance. Now the simple diode where I speak about the silicon diode, it has got a special representation here. When I speak about the silicon diode, you know that all the diodes are either silicon or germanium based diodes, right? So now the very conventional operation of this diode or this rectifier, you know, whenever the input voltage, right, V in goes above the threshold voltage, which is generally 0.7 volts in this particular case, right? So the input itself is represented at the output, right? So more than that, what we are interested rather than your our input and output waveforms, right? If you look at the transfer function, right? So now your output, suppose if this is 0, let us say that this is 1 volt, say this is 2 volts. So up to about 0.7 volts your output will be 0 only, right? So then afterwards your output will increase like this, right? So in fact, if you consider an ideal switching, then probably it would have come something like this. Now I am talking about the practical switching. It is about 0.7 volts. So this is what is your characteristics if you take it with respect to the input and output, the transfer characteristics, right? Why I am telling all these things here is we are talking about the precision rectifier. Suppose if you want to process a signal, I will use the word process here, right? Or if you want to rectify a signal which is say less than 0.5 volts, I have got an input voltage something like this whose amplitude is 0.5 volt. Now can I use this diode here for this particular purpose? That is the reason why I have been speaking about the fact the silicon diode, right? So your silicon diodes are not capable of processing the signals which are generally below 0.7 volts, because the very threshold voltage itself for the silicon diodes for them to become forward bias, it is 0.7 volts. So now there are possibilities that the signals could be having the amplitudes less than 0.5 volts. Under such circumstances, you will be using what we have referred to it as the precision rectifiers, right? Precision, you know what exactly we mean by the word precision. Whenever the amplitude of the input signal is very small also, you should be able to process that signal, right? Or in this particular case, you should be able to rectify that particular signal. That is called as the precision rectifier. Now there are so many applications. Now if you look at a practical example, right? So now your solar PV cells, okay, you know what is the solar photovoltaic cells. Generally, if you consider a solar photovoltaic cell, right, it will produce a maximum voltage of say 0.5 volts, okay. So that is the reason why, in order to have a higher voltage, we connect them in series. If you want to have the higher current requirements, we connect them in parallel. So like that, we will make solar PV modules where many the cells are connected in series and parallel in order to obtain the required voltage and current. Let us say that I got some 12 volts here. So this 12 volts DC, we can definitely convert it into the corresponding AC, because we can have the inverters, right? We can have the converter configuration, we can have the inverter configuration, right? So now, if at all you want to convert this 0.5 volt itself to AC voltage, then your conventional, the diodes cannot be used there. Please try to note here, I am just telling the inverse function of what we are referring here, rectifier. I am not talking about the rectifier here, because I have to convert DC to AC. This will be inverter. Anyway, inverter is also a similar operation to that of rectifier, right? Only thing is that there will be change in the nature of the outputs, right? So in such cases, if at all you want to have the inversion at the very solar cell itself, then probably your conventional diodes cannot be used there, right? So this is one example which I wanted to take, right? So now, like this, there could be so many examples, right? So many examples where in your signals will be having the amplitude less than 0.5 volts, which need to be processed, which need to be rectified, which need to be inverted, wherein your conventional the diodes cannot be used in such cases, right? So you will be able to have the processing of the signal using the operational amplifier circuits. Again, your operational amplifier circuits will come into picture, plus of course your conventional diodes only, right? We will try to see how exactly we are able to materialize this kind of operations, right, using the operational amplifiers as well as your conventional diode circuits, right? So here what we can write here, signals below say 0.7 volts cannot be processed by conventional diodes, right? So to overcome this op-amp circuits with the conventional diodes are used as precision signal processors. So here I have basically talking about, or particularly I am talking about the precision rectifier, right? Again, we have got the different types here. As long as the precision rectifiers are concerned, we have half wave precision rectifier, right, and we have also the full wave precision rectifier. We have half wave precision rectifier as well as the full wave precision rectifier. Okay. Now we will try to see, and here before I go into any specific configuration, right? So what exactly a precision half wave rectifier does, right? So it will deliver an output, right, which depends on magnitude as well as polarity, right? The output depends on magnitude and polarity of input signal, right? Whereas as long as the precision full wave rectifier is concerned, your output depends only on magnitude of input signal. So this is what is very well known to you, right? As long as the precision rectifiers are concerned, or the conventional rectifiers are concerned. Now only thing is that we are adding an adjective here as the precision, wherein we will be concentrating on the signals which are generally less than 0.7 volts or even 0.5 volts, even much less than that, right? Let us try to see how exactly this rectification is possible here. And one more important advantage here, right? As long as you use the operational amplifier here using op amp. Okay, now what advantage we are having apart from the signal processing is, right, we will be having the advantage of the amplification also, right? When you have 0.5 volts AC signal, you can convert it into 0.5 volts DC signal, but you can convert it into 0.5 volts DC signal as well as you can have an amplification. That is, suppose if I have an input signal something like this, if you assume that it is a half wave rectifier, right? So your output will be this much. At the same time, your output can be this much also, because you are using the operational amplifier here. So using the operational amplifier, you have got very important advantages apart from signal processing. Apart from signal processing, the signal can be amplified also. Signal can be amplified also. So this is what is one of the very important advantages going with the operational amplifiers as well as your conventional diodes, right? So you have got a lot of applications here. Let me briefly write down these applications. Later we will see what exactly are these applications. Something called as dead zone circuit. Dead zone circuit, right? As the name itself indicates, dead zone. Dead zone means what? No operation is being done there, right? So if you look at your microcontrollers, very similar to your NOP operations, no operations, right? In order to kill a certain time, you are using the NOP instructions. Similar to that, it is an analogy, right? There is no one-to-one correspondence. So dead zone circuit, for a particular period of time, you are not supposed to get any output. After that, your output should be as desired by you, depending upon the circuit configuration, right? So you have the clippers, right? You know what are clippers? You have the clampers, right? So you have something called as sample and hold circuits. All these things we will discuss as applicable to our curriculum. Then AC or DC converters. So these are some of the important applications of our precision rectifiers, right? You use them in the dead zone circuits, clippers, clampers, sample and hold circuit, as well as AC and DC converters. So this is the brief introduction about what exactly we mean by the dead zone, the precision rectifiers, right? Where do we use them and how do we materialize them, right? So now with this brief background, let us move on to the first circuit, that is the small signal half wave rectifier. It is also referred to as precision half wave rectifier, right? Precision half wave rectifier. And in some cases it is also referred to as small signal half wave rectifier. Both names are used. Small signal, you know why we are using the very word small signal here. Okay, so now let us try to take down the circuit here for the precision small signal or the small signal half wave rectifier. Please look at the circuit. All of you draw the circuit. So I have very importantly here, the other things are very simple. Second, I'll connect it here. Yeah, it has to be connected here only. And here, let me give the input V in. This is only indicative, minus plus. Let me call this voltage as V0 dash. This is your diode D1. It is your traditional or conventional diode, which we use in other cases also. This is my RL. Yeah, this is what is the circuit. All of you please note down. And again, plus VCC minus VEE here. Now I draw the waveforms here. You have the input signal, V in. Now this is the precision half wave rectifier, so therefore you know exactly what happens here. Yeah, this is your V0. This is T. All of you please note down these waveforms. Now, am I audible clearly?
Yes, sir.
Okay, fine. So this is called as the precision half wave rectifier circuit, which is also called as small signal half wave rectifier. Very simple operation. If you understand one concept, one simple concept here, this appears to be a very simple circuit. I hope all of you have noted down this. So now please see, had the diode been absent in this circuit, what this circuit should have been? Can somebody?
Inverting amplifier.
Inverting amplifier. How do you say that it is amplifier? What are the things that are attributed to an amplifier? No resistances here in this circuit except the load resistance. Whenever you want to have an amplifier, the gain should come into picture, no? Whether it is inverting or non-inverting. So for an inverting amplifier, minus RF by R1. For non-inverting, 1 plus RF by R1 represent the gain. But where are RF and R1 here in this circuit? So what this circuit is in the absence of diode? you remove the diode, put a short circuit. What is this circuit? Very simple.
Operational amplifier.
Voltage follower, right? In case of the diode remaining absent here, you would have got the function of a voltage follower, because the input is connected to the non-inverting terminal, the feedback is given from the inverting terminal to the output voltage in case of the diode is absent, right? So now this diode, see, please note that this diode is again a conventional diode only here, right? So this diode D1 has got the threshold voltage of 0.7 volts only, that will not change, right? But still this circuit is capable of processing signals even of microvolts level. Let us try to see how it is possible, right? So now in this particular circuit, right, so the whole operation is again attributed to the nature of the input signal. Let us say that this is the input signal which I have already drawn there, right? So during the positive half cycle, right, so what exactly happens? The diode basically, it acts as an ideal switch. The diode D1 here, it acts as ideal switch, right? So now you can see here, during the positive half cycle, the input starts increasing this way, okay? So when the input starts increasing this way, so here in this particular path, okay, as V in starts increasing, that's what just now I have been telling, V in starts increasing, the output V naught dash also starts increasing in the positive direction. It is by virtue of the operational amplifier, right? So now very importantly here, the voltage drop across the diode, this is a very important point to be noted down, right? So when V in starts increasing in positive direction, V naught dash also starts increasing. Please remember, V naught dash is before the presence of the diode, right? V naught dash is the value of the output voltage before the presence of the diode, whereas your V naught is the actual output voltage, right? So when the diode D1 becomes forward bias, now you may ask, the diode requires 0.7 volts to become forward biased, but in this particular case, since the diode is connected in the forward loop, you can see here the diode is connected this way, is it not? So this diode is connected this way, and this completes the feedback path from here. So this completes the feedback path. Now what exactly happens here is, the voltage drop, right, is divided by the open loop gain of the operational amplifier, right? So when the diode is forward biased, here I will go little lengthily, because this is the concept which you can understand later. The different applications on the basis of these concepts you can easily understand, right? So when the diode is forward biased, the voltage drop across the diode gets divided by the open loop gain of. Now you can see here, you have got the open loop gain. whatever the voltage drop you are going to have across the diode, right, it is going to get divided by the open loop gain. Suppose now the voltage has reached say some 0.5 volts or something like that, or 0.3 volts, right? So you know what is the open loop gain, AOL, of an operational amplifier. Typically, if you consider IC 741, it is going to be 50,000, right? So suppose if you divide this 50,000 by 0.5, you can see this will be definitely available in the form of microvolts. So this particular feature makes the voltage across the diode to get greatly reduced by a factor of the open loop gain, and the diode starts following the voltage V0 dash here, whatever we are having here, right? So when the diode D1 is forward biased, so it closes the feedback path. The diode thus closes the feedback path. This is what is required for us. The diode thus closes the feedback path, and now this diode, once the feedback path is closed, it acts as a voltage follower. The diode acts as a voltage follower. So now when the diode acts as a voltage follower for the entire positive half cycle, you are going to get an output voltage like this, what I have shown here, right? So that doesn't require the voltage across the diode to be 0.7 volts. Remember, since the diode comes in the forward path, the voltage across the diode gets divided by the open loop gain, which is very high in case of the operational amplifier. So therefore, the very condition of satisfying the VT of 0.7 volts doesn't hold good here. The diode becomes forward biased. So you are going to get the loop closed here, right? Next here, after that, you can see here now. So during the negative half cycle, right? During negative half cycle, so what exactly happens? The input voltage will now become negative or minus, right? So your V in is negative. During the negative half cycle, your V in is negative, and of course your V0 dash also increases in negative direction. V0 dash also increases in the negative direction. So when, how long it will increase? Till it is equal to minus VEE. So this is what is the switching that is taking place between plus VCC and minus VEE, right? So it will go in the negative direction till it reaches minus VEE, and once it reaches minus VEE, the diode is now reverse biased. The diode is reverse biased. So this opens the feedback loop, so that you can see here, right? So when the voltage reaches in the negative direction, right, the diode becomes reverse biased, and you will not get any output from this point to this point. So this is how you are going to get the operation of a precision half wave rectifier, and so here this will give you V0 is equals to 0 during the negative half cycle, right? Now, having said this, right, so we have already seen how exactly this circuit operates. During the positive half cycle, the diode becomes forward biased, so the voltage across the diode gets divided by the factor of the open loop gain. So that is the reason why it starts conducting. During the negative half cycle, the diode will be reverse biased because of the reverse voltage. So now, even though we say like this, there are certain important conditions to be fulfilled here, because the diode has to continuously switch in and switch out, because these cycles, whatever I have shown here, these cycles depend upon the input frequency, correct or not, right? So whatever the input signal we are having there, that depends upon the input frequency. Very quickly it will go to a positive side, then again it will come back to the negative side. So when you have the diode, you just imagine the diode conduction also has to accordingly change in such a fast manner. So the forward biased diode should become reverse biased, again it should become forward biased, again it should become reverse biased in a very quick time. So it is not as simple as what we say there. So how do you bring the diode into forward bias? How do you make it to come to the reverse bias? You have to make the charge carriers to recombine. Negative voltage should come across the diode, then it will become completely reverse biased. So there are so many other conditions to be satisfied in making the diodes to become forward biased and reverse biased. So therefore, we will not be able to use the conventional diodes here, what we are using in our applications, in our conventional applications, right? So basically the switching, right? So the op amp here, you can just write the op amp in such circuits, the op amp in such circuits should be a high speed op amp, and the diodes used must also fulfill certain requirements in order to have the high speed operation, right? So one thing is that when the input frequency or when the input signal is dependent on the frequency, the operational amplifier also should switch between the positive and negative half cycles so quickly, right? Because the diode is present in the series of the feedback path, and at the same time your diode also should fulfill certain important conditions. Anyway, when we look at the design parameters there, that time it is easy for us to understand what are the desirable characteristic features of the diode, right? So your IC 741 and cannot be used here, right? They are not the high speed operational amplifier. There are so many high speed operational amplifier like mu A318, right? So that is one high speed operational amplifier. Then you have got HA2500, LM310. These are all the high speed operational amplifiers. So these operational amplifiers must be used in order to make sure that your precision rectifier circuits operate properly, right? So this is what is the understanding what you are supposed to have as long as the precision half wave rectifier is concerned. Now let us try to look into one more configuration here itself, right? Suppose if you want to have, you can just note down this waveform also if you want, right? So I have the input signal something like this. So this is V in. Now I want the output to be like this. I want the output to be like this. So what suggestions or what modifications do you suggest here in the previous circuit? You should be quick enough here. If you have understood the previous circuit, you should be able to tell me the answer for this. So here your D is on, so your D is off here. What changes you have to make? Can anybody?
Diode direction should be
Yes,
changed.
very good. The direction of the diode has to be changed, right? So now your diode should come this way. That's all. So these type of things are asked in your competitive exams and all, right? You may have the circuit given like this. You will be given 4 different options of the waveforms, so you will have to choose the appropriate one. If you have the idea, then within no time you should be able to tick the right answer. Am I right now? So now this is how your diode is connected, and this is very easily understandable also. If at all you want to obtain the waveform like this, the diode is connected. During the positive half cycle, your D1 is reverse biased, right? So therefore during positive half cycle, D1 is reverse biased and your output V0 is equal to 0. During the negative half cycle, D1 is forward biased, so your V0 is equals to VA. This is what is the simple understanding or simple explanation for the circuit which we have drawn here, or the waveform which we have drawn here. Is that fine? All of you have drawn this?
Yes, sir.
Okay. So now let us try to see, okay, the basic rectification plus amplification. So as long as you have the voltage followers, what we have been seeing in this particular frame or in the previous frame, whatever we have seen, the rectification is possible depending upon your requirement, half wave rectification of course, right? But you are not able to have the amplification because we are not using the inverting or non-inverting amplifier there, right? So now we will try to see if at all your circuit necessitates to have an output with the rectification as well as with the need of amplification, right? So what we can do, right? So that's what we will see now. That is half wave precision rectifier, half wave precision rectifier, so which is inverting type. Let us start with the inverting type. Later we can try to modify it to the non-inverting type or something like that, right, if required. So let me draw the circuit for this. As usual, I should have an operational amplifier, then when I say that I have the inverting type, here I have connected it to ground like this, then I have input. Please try to see what I am drawing here, which of course you have already done earlier. Okay. So now this I am trying to connect to the inverting terminal here. Now here I will have one diode, this I am connecting here, followed by that I have one more diode, and of course here I have one load resistance, so this is my V in. Now you see here, this is R1, this is RF, let us say that this is R3. So this RF I will write it as R2 because my further explanations also take it as R2. This is RL. So this is my V0 dash and this is my V0. R3 either you can have or you may not. Again, coming back to the waveforms, this is my V in. So let me draw the output waveform later after having understood the operation here. This is my V0. Okay, have you drawn this? Now two diodes are required here. Please try to understand this circuit because I am trying to use the gain factor also here in this example. So that is the reason why this is plus VCC, this is minus VEE. Even if you don't write also it is fine, but it's better you write it, right? So now what is the circuit operation here? How do you analyze the working of this particular circuit, right? So let us start with this point as usual. When the input voltage is greater than 0, right? When V in is greater than 0, what happens? Your input voltage is positive here, right? So when the input voltage is positive, the current here, let us say that the current, the input current I1 flows through R1. So what will be the value of V0 dash now? Can somebody tell me? It is negative because we are using inverting. It is basically used as the inverting amplifier, right? So now when this V0 dash is negative, okay, when V0 dash is negative, this is the important point for you to note down, right? So when this is negative, so definitely this diode D2 will be reverse biased. So this negative voltage has come to the cathode here. So therefore your D1 will be forward biased. D1 is forward biased. D2 is reverse biased. D2 is reverse biased. So when D2 is reverse biased, so from here to here you don't expect any output, right? That is the reason why I have drawn with a dotted line, which I will remove. That again, that will be confusion for you, right? So you will not be having any output during the positive half cycle of the input signal, right? So now the second part, when V in is less than 0, the input is negative, right? When V in is less than 0, input voltage is negative, so therefore obviously your V naught dash is positive because it's an inverting amplifier. So when V naught dash is positive here, okay, so your D2 is forward biased, and of course your D1 is reverse biased. Now the op amp acts as a inverting amplifier. You will get the operational amplifier acting as an inverting amplifier. So you will get the output here. So this is the condition which represents D1 off and D2 on. So D1 off, D2 on. This is the condition where you are going to get this particular case. This is very simple for you to understand. Now here your V naught is equals to minus R2 by R1 into Vi. So that is the reason why I have been telling here. So you will be having the operation of this circuit both as the signal processing circuit, that is the rectification, as well as the amplifier, right? So now if you select the value of R1 and R2 in such a way that you can get a positive gain, right? You can get a gain more than one. You can amplify the signal as well. So therefore, if you take the output input something like this, right? Your output could be either this way or your output could be either this way, depending upon your gain value there, right? So this is what is the advantage of going with either inverting or non-inverting type of these configurations. And here as long as the design of the circuit is concerned, right? So we will have to take care one important point. Whenever the diodes have come into picture, all other design will remain similar to what we have done for an inverting amplifier, right? So you take the gain, then you take the ratio of R2 and R1. Your R3 will be parallel combination of R1 and R2, which is generally equal to the lower value. All those things hold good as per the requirement of an inverting amplifier. But apart from that, you will have to look into one more parameter, the design related to the diodes. The peak inverse voltage, can you recall something? When I say peak inverse voltage, what is peak inverse voltage? It is the voltage across the diode in the reverse direction when the diode is conducting, right? So the peak inverse voltage should be, see, suppose if your VCC is 6 volts, VEE is minus 6 volt, the diode used here should have a peak inverse voltage of plus VCC minus of minus VEE, that is 12 volt. This is a very, very important point to be noted, right? It should be greater than or equal to plus VCC minus of minus VEE. When we solve the problem, we will try to see this. And the reverse recovery time, I have already told you about this, TRR, because the diodes should come from the positive conduction state to the blocking state. We should allow certain time for the charge carriers to recombine there. So that should be always, the reverse recovery time should be always equal to or greater than T divided by 10, where T is the time period of the input signal. All other things will hold good as applicable to your inverting amplifier, but when it comes to the diodes, these 2 points are to be taken care. Anyway, we will try to solve one example on this in our next class. That time it will be clear to you.